Why will humanity never set foot on Mars? There is an idea that returns to my thoughts again and again, one that feels deceptively simple until you pause and truly examine it. The idea of sending human beings to Mars. It is often spoken about as if it were almost inevitable, nearly routine. NASA speaks of it. SpaceX speaks of it. China speaks of it. There is a widespread assumption that Mars is the next natural destination for our species. Yet, from the perspective of physics, this is where the story becomes genuinely astonishing. When you sit down and calculate what is actually required, when you examine the energies involved, the vast distances, and the immense timescales, it becomes clear that this may be the most demanding challenge humanity has ever set for itself. Not simply demanding because it is costly or technically complex, but demanding because the underlying laws of physics themselves appear to resist us at every step. Going to the moon was difficult. We often reflect on how the Apollo program accomplished something extraordinary using technology that now seems almost archaic. But Mars belongs to an entirely different category of difficulty. If reaching the moon was like climbing a steep hill, then reaching Mars is like climbing Everest, carrying another person on your back, in winter, relying on equipment that may or may not function at the precise moment you need it most. At the heart of the challenge lies distance. The moon circles Earth at an average distance of around 384,000 kilometers. Light covers that gap in about 1.3 seconds. The Apollo astronauts took roughly 3 days to make the journey. You could carry enough food and water for a short trip, bring reserves of oxygen, and take comfort in knowing that if something went wrong, home was only 3 days away. Mars transforms that entire equation. At its closest possible approach to Earth, when both planets happen to be on the same side of the Sun in near-perfect alignment, Mars remains about 55 million kilometers distant. That is the most favorable situation imaginable, and it occurs only once every 26 months. At the other extreme, when the Sun lies between Earth and Mars, the distance stretches to more than 400 million kilometers. On average, the separation you would contend with during a mission is about 245 million kilometers. To grasp what that means, even at its closest, Mars is roughly 140 times farther away than the Moon. At average distance, it is nearly 600 times farther. These figures are not abstract curiosities. They have profound consequences. They dictate travel times that redefine how missions must be designed. You cannot simply aim a rocket at Mars and keep the engines firing until you arrive. Doing so would demand quantities of fuel that are, for all practical purposes, impossible. Instead, spacecraft follow what are known as Hohmann transfer orbits, carefully chosen minimum energy paths that allow gravity to do much of the work. You depart Earth and enter an elongated orbit around the Sun, one calculated with exquisite precision so that its farthest point intersects the orbit of Mars at the exact moment Mars arrives there. This journey takes approximately 7 months. 7 months drifting through interplanetary space, moving silently along your orbital path, watching Earth fade into the distance as Mars slowly grows ahead. The Apollo astronauts were away from Earth for about 8 days. A crew bound for Mars would be absent for no less than 2.5 years, 7 months to travel outward, possibly a year or more on the Martian surface, waiting patiently for the planets to realign, followed by another 7 months for the return journey. Some mission designs extend to 3 years or beyond, depending on the chosen trajectory. Crucially, you do not decide when to go. The architecture of the solar system sets the schedule. Earth completes an orbit of the Sun in about 365 days. Mars takes roughly 687 Earth days, moving more slowly because it lies farther from the Sunday. Favorable alignment for a Hohmann transfer occurs only once every 26 months or so. Miss that window, and you wait more than 2 years for the next chance. This stands in stark contrast to lunar missions, where the Moon's 27-day orbit around Earth allows launches at almost any time. For Mars, the universe itself dictates the timetable. This 26-month rhythm sends ripples through every aspect of planning. Your spacecraft must be ready precisely on time. Your crew must be fully prepared and medically fit. Supplies must be loaded, systems tested, trajectories finalized. If a critical component fails late in preparation, if testing reveals an unforeseen flaw, if funding is delayed or a vital technology is not yet mature, you do not slip the schedule by weeks. You slip it by 26 months. And during those 26 months, hardware ages, budgets come under strain, political will can falter, and teams may fragment. The pressure surrounding a Mars launch window is unlike anything experienced in human spaceflight, because the penalty for missing it is counted in years rather than days. Distance introduces another challenge, one that is less immediately obvious but just as formidable: communication delay. On Earth, we are accustomed to near instantaneous conversation. Even exchanges with astronauts aboard the International Space Station are delayed by less than a second. With the Moon, the round-trip communication time is about 2.6 seconds. You can almost hold a normal conversation with only a faint, slightly uncomfortable pause between sentences. Mars shatters that illusion completely. Even light, the fastest messenger the universe allows, requires between 3 and 22 minutes to cross the space between Earth and Mars, depending on how the two planets are arranged along their orbital paths. At their closest encounter, you send a message and wait 3 minutes for it to reach its destination. Any reply then needs another 3 minutes to return. That gives you a best-case round trip of 6 minutes. At the other extreme, when Mars lies on the opposite side of the Sun, any exchange of information suffers a delay of 44 minutes. And for extended periods during each orbit, when Mars slips behind the Sun as seen from Earth, communication stops altogether. The Sun's radiation overwhelms and silences every signal. Now consider, carefully, what that implies for a crew living on Mars. If an astronaut faces a serious emergency, there is no possibility of calling mission control and receiving guidance in real time. They identify the problem, send a description, and then wait. 3 minutes pass, 10 minutes, 20 minutes go by before anyone on Earth even realizes something has gone wrong. Mission controllers study the situation, debate the options, decide on a response, and transmit it back. More minutes slip away. By the time any advice arrives, the crisis has either been solved entirely by the crew's own ingenuity, or it has already taken their lives. The immediate support that has defined human spaceflight since its earliest days simply does not exist on a Mars mission. During the Apollo 13 accident, astronauts and mission control worked together continuously, exchanging ideas, testing solutions, and adapting second by second as events unfolded. That shared problem-solving, that uninterrupted dialogue between Earth and spacecraft, saved 3 human beings. On a mission to Mars, the crew must be prepared to face every emergency alone, with guidance that arrives only after the most crucial decisions have already been made. They will experience a degree of solitude no human has ever known. And this isolation is not merely technical. It reaches deeply into psychology, in ways we are only beginning to grasp. Aboard the International Space Station, astronauts glance out of the window and see Earth filling their field of view, blue and white and exquisite, unmistakably close, unmistakably home. They can speak with their families by video, watch live broadcasts, and remain tethered to life on the surface below. The station circles just 400 kilometers above Earth. Mars, by contrast, lies hundreds of millions of kilometers away. During the journey outward, Earth diminishes steadily, day after day, week after week. It contracts in the window. Within a short time after departure, it is no longer a disk marked by oceans and continents. It becomes a single bright point, brighter than most stars, yet fundamentally no different from them, no longer recognizably a world. The crew will only be able to see Earth through telescopes. Eventually, for parts of the voyage, it will vanish entirely into the glare of the Sunday. Everything they know, everyone they love, every place they have ever walked is reduced to an unseen dot lost somewhere in the darkness. We do have some experience with isolation in extreme settings. Research stations in Antarctica shelter, small teams through months of winter night, cut off from the rest of humanity by weather so severe that evacuation is impossible. Submarine crews live for months beneath the ocean, without sunlight, and with tightly limited communication. These situations teach us something about how people endure confinement and separation. But the comparison only goes so far. The teams in Antarctica know that summer will return. Aircraft will eventually land. Submarine crews can surface if necessary and head back to port if a crisis becomes unmanageable. Crews bound for Mars have no such escape. Once they depart Earth orbit, they are committed to a voyage measured in years, with no option for an early return. No matter what occurs, the spacecraft itself must keep them alive for 7 months of travel in each direction. Every breath consumes oxygen that must either be transported from Earth or regenerated from exhaled carbon dioxide. Every meal draws down stores that cannot be restocked. Every drop of water must be captured, reused, and recycled from moisture in the air, from washing, and from urine. Nothing can be wasted. The space station receives regular resupply missions, with fresh food, new equipment, and replacement parts arriving from Earth every few months. A spacecraft heading to Mars carries everything required for the entire expedition. If a component fails and the replacement was not brought along, there is no possibility of requesting another. This leads to what engineers describe as the tyranny of the rocket equation, and it governs every detail of planning a Mars mission. The link between the speed you wish to achieve and the fuel needed to reach it is not linear, it is exponential. Increase the desired velocity slightly, and the required fuel rises dramatically. That fuel itself has mass, and accelerating that additional mass demands even more fuel. The mathematics escalate relentlessly. For a mission to Mars, every kilogram of food, every liter of water, every spare part, every scientific instrument translates into many additional kilograms of propellant needed to accelerate the spacecraft and then slow it down again at its destination. Mission designers are forced into harsh choices about what can be carried and what must be left behind. Every object must earn its place. Redundancy is vital for survival, but it comes at a heavy fuel cost. Items that might ease the crew's psychological burden compete directly with instruments that would increase scientific return. The margins are narrow, the compromise is severe, and the price of a mistake could be death. This is why a Mars mission cannot simply be an enlarged version of Apollo. It is not just a question of building a larger rocket and loading more supplies. The physics itself changes in character when mission durations stretch from days to years and distances expand from hundreds of thousands of kilometers to hundreds of millions. Every system must be redesigned to function reliably over timescales longer than anything humanity has yet proven possible. Every consumable has to be stretched, repurposed, or recycled in ways we are only beginning to understand. Every emergency protocol must be designed around the stark reality that real-time assistance from Earth is impossible. And that is before we even consider what confronts us when we finally reach Mars itself. We have not yet grappled with the ordeal of landing on a world whose atmosphere is too thin to offer much help, yet thick enough to be dangerously unforgiving. We have not fully explored the hazards of toxic soil, the relentless cold, or the radiation that persists even on the surface. Nor have we faced the deeply unsettling problem of leaving Mars again, of launching from another planet to make the journey home. The voyage to Mars is not impossible because the laws of physics forbid it. They do not. The mathematics works, the equations resolve, the trajectories close. It is impossible in another sense. It demands that we solve problems humanity has never solved, that we construct systems more reliable than anything we have ever built, and that we prepare astronauts for a level of isolation more complete than any human has ever known. Every element of the mission presses hard against the outer limits of our capability. The moment you depart Earth orbit and set course for Mars, you enter an environment that is profoundly hostile to human biology in ways that have no parallel on our planet. The interplanetary medium, that immense emptiness between worlds, is saturated with radiation that our bodies never evolved to endure. On Earth, we are shielded by two invisible protections we rarely stop to notice. Our atmosphere absorbs much of the incoming radiation before it ever reaches the ground, and Earth's magnetic field deflects charged particles from the sun and from deep space, guiding them toward the poles where they paint the auroras rather than falling upon us everywhere. When astronauts travel to the International Space Station, they remain within Earth's magnetic field and retain much of that protection. Low Earth orbit is comparatively benign in terms of radiation. The doses are higher than on the surface, but they are manageable for missions that last months. But astronauts bound for Mars leave all of that behind. Once beyond Earth's magnetic influence, they are exposed to the full radiation environment of interplanetary space. And there are two distinct dangers to consider. The first comes from the Sun itself. Our star continuously releases a flow of charged particles known as the solar wind, and from time to time, it unleashes something far more violent. Solar flares and coronal mass ejections can hurl vast bursts of high-energy particles outward through the solar system. These solar particle events are inherently unpredictable. We can watch the Sun, track active regions on its surface, and sometimes anticipate heightened activity, but certainty eludes us. When such an event occurs, the particle storm can arrive within hours. The Apollo astronauts were extraordinarily fortunate. Their missions lasted only about 8 days, and none coincided with a major solar particle event. The odds of encountering a powerful solar storm during such a brief interval were relatively small, and chance was on their side. A journey to Mars, however, takes 7 months each way. The likelihood of avoiding all significant solar activity over 14 months of interplanetary travel is far lower. From a statistical standpoint, a Mars crew is likely to experience at least one major solar event during the mission. If they are outside the shelter of a planetary magnetic field, when such a storm strikes, the radiation dose could be severe, potentially fatal, without sufficient shielding and timely warning. The second threat is subtler and more troubling because it never ceases. Galactic cosmic rays are extremely high-energy particles that originate beyond our solar system, accelerated to astonishing speeds by supernovae and other catastrophic cosmic events. They arrive from all directions, all the time, an unending drizzle of radiation that cannot be predicted or avoided because it is always present. These particles are extraordinarily penetrating. The most energetic cosmic rays can carry more energy in a single particle than a baseball thrown by a professional pitcher. When they strike matter, they do not stop easily. This leads to a counterintuitive challenge when it comes to shielding. For lower energy radiation, adding more shielding usually helps. The particles collide with the shield and deposit their energy there rather than in the body. But when galactic cosmic rays hit shielding material, they can fracture atomic nuclei and generate cascades of secondary particles. This process, known as spallation, means that thin shielding can actually worsen the problem. You may block some of the primary radiation, only to create a spray of secondary particles that are themselves dangerous. Beyond a certain point, adding conventional shielding becomes counterproductive. The most effective shielding materials against cosmic rays are rich in hydrogen. When cosmic rays strike hydrogen nuclei, which are single protons, they do not produce large amounts of secondary radiation. Water performs reasonably well as a shield. Polyethylene, the plastic found in everything from shopping bags to cutting boards, is in fact more effective than metal for radiation protection. Some mission designs propose surrounding crew habitats with water tanks, allowing them to serve two purposes at once, supplying drinking water while also providing radiation shielding. Other concepts involve polyethylene blocks or panels infused with hydrogen-rich materials. Yet, even the best shielding only reduces exposure to cosmic rays. It does not remove it. The accumulated radiation dose from a round trip to Mars is genuinely worrying. Current estimates indicate that astronauts would receive somewhere between 0.3 and 1 sievert over the course of a full mission, depending on solar activity and the effectiveness of the shielding. For comparison, an average person living on Earth absorbs roughly 3 millisieverts each year from natural background radiation. An astronaut traveling to Mars could receive the equivalent of 100 to 300 years of normal background exposure, compressed into a period of about 2.5 years. That kind of dose does not cause immediate illness, but it does substantially raise the lifetime risk of cancer, possibly by several percentage points. This is not about acute radiation sickness, not the dramatic effects that follow extremely high doses over a short time. It is about probability, the quiet increase in the chance that cancer may appear many years, even decades, after the exposure. Space agencies already impose lifetime limits on how much radiation an astronaut is allowed to receive over a career, and a single mission to Mars could come very close to those limits, or even exceed them. For that reason, some mission planners have suggested that the first crews to go to Mars might be older individuals, people who have already had children, for whom the long-term cancer risk carries slightly less weight simply because there are fewer remaining years for the disease to emerge. It is a bleak calculation, but it reflects the realities of interplanetary travel with the technology we have today. Radiation is one invisible danger. The lack of gravity is another, and its effects on the human body are deep and wide-ranging, many of them still not fully understood. Every system in your body evolved under the constant pull of Earth's gravity. Your bones, your muscles, your heart, your eyes, your inner ear, all developed to operate in an environment of one gravity. Remove that gravitational pull, and the body begins to change, sometimes in ways that are merely inconvenient, and sometimes in ways that could threaten the success of a mission. The most obvious change is muscle atrophy. On Earth, your muscles are always working against gravity, simply to keep you standing and moving. In microgravity, that demand disappears. Muscles that are no longer used begin to shrink, and they do so with remarkable speed. Without countermeasures, astronauts can lose around 20% of their muscle mass within 2 weeks of arriving in space. On board the International Space Station, astronauts follow a strict exercise regime, spending roughly 2 hours every day using specially designed equipment. They run on treadmills while wearing harnesses that pull them down toward the running surface, and they use resistance machines built to mimic the effects of weightlifting. This demanding routine slows muscle loss, but it does not stop it completely. Astronauts returning from missions lasting 6 months often need help just to walk. Some describe the sensation as if their legs suddenly weigh 1,000 pounds when they are back under Earth's gravity. Bone loss is even more troubling because it is far harder to undo. Your skeleton is not a fixed structure. It is constantly being renewed, with old bone broken down and new bone formed in response. This balance depends on mechanical stress. When you walk, run, or simply stand, you place stress on your weight-bearing bones, and your body maintains their density accordingly. Take that stress away, and the balance shifts. Bone breakdown continues, but new bone formation slows dramatically. In space, astronauts lose bone mass at a rate of roughly 1 to 2% per month in weight-bearing regions such as the hips, the spine, and the legs. Over a 6-month mission, that can amount to a loss of 10% or more in critical areas. Unlike muscle, which can be rebuilt relatively quickly after returning to gravity, bone recovers very slowly. Studies of astronauts coming back from long-duration missions suggest that some of the lost bone density may never be fully regained. They return with skeletons that are permanently weaker than when they left. When you consider a mission to Mars, the figures become genuinely worrying. Around 7 months of travel outward, followed by a stay on the surface in Mars gravity, which is only 38% of Earth's, and then another 7 months for the journey home. The total time spent in reduced gravity could approach 2 years or more. We simply do not know what this would do to the human skeleton, because no one has ever experienced these conditions. Mars gravity might slow bone loss during the surface phase, but we have no direct data on how the human body responds to partial gravity. Every measurement we have comes either from full Earth gravity or from the near-zero gravity of the space station. Everything in between remains unexplored. The cardiovascular system also adapts to microgravity in ways that could cause serious issues on arrival at Mars. Without gravity to push against, the heart does not need to work as hard. Blood that would normally pool in the legs shifts upward, accumulating more in the head and chest. The body interprets this as an excess of blood volume and responds by reducing it. Astronauts in space actually carry less blood than they did on Earth. Over time, the heart itself can change shape and may weaken due to the reduced workload. Some researchers are concerned about what happens when this adapted system is suddenly required to function again under gravity. Will a heart conditioned by months in microgravity cope effectively with Mars gravity? One of the more unexpected findings from space station research involves vision. A significant proportion of astronauts, perhaps 30% or more on long-duration missions, experience changes in their eyesight. Some become more farsighted. Others develop swelling of the optic nerve. In some cases, the back of the eye actually flattens, altering how light is focused. This collection of symptoms is known as spaceflight-associated neuroocular syndrome, and its underlying cause is still not fully understood. The leading explanation, again, involves fluid redistribution. With more fluid shifting toward the head, pressure inside the skull increases. That pressure may affect the optic nerves and the structure of the eye itself. On missions lasting 6 months, these changes often reverse after a return to Earth. On a Mars mission lasting several years, we do not know whether the damage would become permanent. Could astronauts reach Mars with severely impaired vision? Would they still be able to perform complex tasks on the surface? Would the condition continue to worsen over time? These questions remain unanswered. The immune system also behaves in unusual ways in space. Some immune responses become overactive, leading to increased inflammation, skin rashes, and allergic reactions. Other responses are suppressed, potentially leaving astronauts more vulnerable to infections. At the same time, some microorganisms appear to become more aggressive in microgravity, more capable of causing disease. On the space station, this situation is manageable because serious medical emergencies can be dealt with by evacuating crew members or sending urgent resupply missions. On Mars, that option simply does not exist. Evacuation is impossible. If an astronaut were to develop a severe infection that fails to respond to the antibiotics carried on board, the consequences could be fatal. And yet, there may be a way to address many of these physiological challenges. The idea is beautifully simple in theory, even though implementing it is anything but simple. Artificial gravity. By setting a spacecraft into rotation, centripetal acceleration can mimic the pull of gravity. Spend the journey inside a rotating section of the vehicle, and your body begins to experience something approaching normal gravity, or at least a meaningful fraction of it. Muscles are given resistance to work against. Bones are subjected to mechanical loading once again. Bodily fluids redistribute in a more natural way. The cardiovascular system operates in a state far closer to its normal function on Earth, but the engineering hurdles are formidable. A rotating spacecraft is inherently more complex than a non-rotating design. The rotation rate and the radius of the rotating section must be chosen with great care, strong enough to provide useful gravity, yet slow enough to avoid disorienting Coriolis effects. That rotating habitat must also be linked to non-rotating sections that house communication antennas and solar panels, requiring sophisticated joints and seals. Mass increases, and that increase propagates through the rocket equation, demanding more fuel. Costs rise accordingly. But the alternative is to send astronauts on a journey that will steadily damage their bodies in ways we cannot yet fully predict or entirely counteract with other measures. When weighed carefully, the balance between engineering complexity and crew health may well tip in favor of artificial gravity for missions to Mars, despite the added expense and difficulty. We are still refining the concepts, still conducting experiments, still building prototypes, and still learning exactly how to make such systems viable. After 7 months of travel through interplanetary space, enduring radiation exposure, and progressive physical decline, the spacecraft finally nears Mars. And then comes what may be the most frightening stage of the entire mission: landing. NASA engineers refer to it as the 7 minutes of terror, and that phrase is not an exaggeration. It is a precise description of the challenge of placing a spacecraft safely onto the Martian surface. The core of the problem lies with the Martian atmosphere. Unlike the Moon, Mars does have an atmosphere, but in many ways that makes things worse, not better. At the surface, atmospheric pressure on Mars is about 600 pascals. By comparison, Earth's atmosphere at sea level measures around 101,000 pascals. Mars possesses less than 1% of Earth's atmospheric density. This ghostly thin layer of air creates a unique engineering dilemma because it is simultaneously too much and too little. When a spacecraft arrives from interplanetary space, it is moving at roughly 20,000 kilometers per hour relative to Mars. That is about 5.5 kilometers per second. That enormous speed must be reduced to zero gently enough to avoid destroying both the spacecraft and its cargo. On an airless body like the Moon, rockets do all the work. Engines fire continuously until all velocity is removed and the vehicle settles softly onto the surface. It demands large amounts of fuel, but the physics is straightforward. On Earth, the dense atmosphere takes over much of the job. A spacecraft entering the atmosphere experiences immense drag. Air resistance slows it down, transforming kinetic energy into heat that is absorbed by a heat shield. By the time the vehicle descends through the atmosphere, most of its velocity has been removed. Parachutes then deploy, slowing the craft further to speeds that allow for a safe landing, either with a brief, final rocket burn or by impacting land or water at a survivable speed. Mars offers neither solution cleanly. Its atmosphere is thick enough to generate extreme heating during entry. A heat shield is absolutely essential, as temperatures can exceed 1,500 degrees Celsius when the spacecraft plows into the Martian air, yet the atmosphere is far too thin to slow the vehicle sufficiently. After surviving the entry and heat shield phase, the spacecraft may still be traveling at around 1,500 kilometers per hour. That is roughly Mach 2 under Martian conditions, still supersonic, still lethal on impact. Parachutes are then deployed, and this is where the thin atmosphere reveals its betrayal. Parachutes rely on drag, and drag depends directly on atmospheric density. In Mars's tenuous air, even the largest parachutes we can engineer only slow the spacecraft to a few hundred kilometers per hour. That is still faster than a commercial airliner cruising at altitude. Landing at that speed is impossible. Survival at that speed is impossible. Rockets are therefore required after all, engines that fire in the final moments to eliminate the remaining velocity just before touchdown. Every successful Mars landing has depended on some combination of these methods. A heat shield for initial entry, parachutes for intermediate deceleration, and rockets for the final descent. The Viking landers, in the 1,970 seconds, achieved this. Pathfinder followed. Spirit and Opportunity succeeded as well. Curiosity introduced the remarkable sky crane maneuver, lowering the rover on cables from a hovering rocket platform. Perseverance repeated the same approach. Each landing stretched the limits of what we were capable of at the time. Yet there is a fundamental constraint that cannot be ignored. All of these successful missions delivered relatively small payloads. Curiosity weighed about 900 kilograms. Perseverance was much the same. These remain the heaviest objects we have ever placed safely on the Martian surface. They represent the absolute upper boundary of what our entry, descent, and landing technology has been able to manage. The parachutes were vast. The rockets were immensely powerful. The entire sequence was balanced right at the very boundary of what was possible. There was essentially no room to accommodate anything heavier. A human mission to Mars demands landing something vastly more massive. The precise numbers depend on how the mission is designed, but even the most stripped-down, rudimentary landing scenario would still require delivering at least 20 metric tons to the Martian surface. More credible plans push that figure to around 40 tons, and the most fully developed mission concepts rise to 100 metric tons or more, once you account for living modules, life support, supplies, surface vehicles, scientific instruments, and essential infrastructure. That represents between 20 and 100 times the mass of the most capable Mars lander we have ever successfully deployed. And at present, we simply do not know how to achieve this. Not with technology that has been proven through flight. The parachute systems that work for payloads of 1 metric ton cannot be scaled up to manage 40 metric tons. The laws of physics simply do not allow that kind of linear scaling. A parachute capable of meaningfully slowing a spacecraft weighing 40 metric tons in Mars's tenuous atmosphere would need to be absurdly large. Even then, it would almost certainly fail to provide sufficient deceleration. The structural stresses would be immense, and the dynamics of deployment would be unlike anything humanity has ever attempted. The most promising concept for landing extremely large payloads on Mars is known as supersonic retropulsion. Rather than depending primarily on parachutes, this approach involves firing rocket engines while the spacecraft is still moving faster than the speed of sound, using raw thrust to slow the descent. SpaceX has demonstrated this technique on Earth by landing Falcon 9 boosters, reigniting their engines moments before touchdown. The Starship vehicle is fundamentally built around this idea, relying on its engines throughout the final descent instead of parachutes altogether. But attempting this on Mars introduces a far greater level of complexity than doing it on Earth. The Martian atmosphere is thin and behaves in unfamiliar ways. The interaction between rocket exhaust and a supersonic airflow creates aerodynamic effects that are extraordinarily difficult to predict and have never been tested under actual Martian conditions. When a rocket engine fires directly into an oncoming supersonic airstream, shock waves form and interact in intricate, unpredictable patterns. These interactions can compromise the stability of the vehicle. Heating distributions shift in unexpected ways. While we have conducted computer simulations and ground-based experiments, no spacecraft has ever executed supersonic retropulsion on Mars. The first attempt, likely using a relatively crude vehicle, will be a true experiment, and the entire landing process must operate without human control. This is where the communication delay becomes crucial. When a spacecraft begins atmospheric entry at Mars, mission control on Earth receives confirmation that entry has started. 7 minutes later, the spacecraft has either landed successfully or been destroyed. Yet confirmation of that outcome does not reach Earth until at least 3 minutes after the event itself. During periods of high mission activity or unfavorable orbital alignment, the delay can be significantly longer. Engineers watch telemetry streams that represent events already long past. They learn whether the spacecraft survived only after the outcome has been sealed. During those 7 minutes, there is nothing they can do. No commands can be sent, no corrections can be made, no problems can be fixed. The spacecraft must manage every aspect of the descent on its own, reacting instantly to real conditions, adjusting its behavior, and resolving unexpected anomalies. The onboard software must be virtually flawless, because there is no opportunity for human intervention. If a sensor produces an abnormal reading, the computer must determine whether to trust that data or switch to a backup system. If the descent velocity becomes excessive, the computer must decide precisely when to ignite the engines and how much thrust to apply. If the designated landing zone proves more dangerous than anticipated, the system must recognize the risk and select an alternative site. Every decision is made autonomously. Every result is irreversible, and humans only discover what happened after it is already finished. If the landing succeeds, if astronauts finally step onto the surface of Mars, they will find themselves in one of the most hostile environments anywhere in the solar system. Not hostile in the way Antarctica is hostile, or the Sahara Desert is hostile. Those are extreme places, but humans can survive there with adequate preparation. Mars is hostile in a deeper, more fundamental sense. Mars is actively lethal through multiple mechanisms acting at the same time, and the only thing separating an astronaut from death is the equipment they bring with them. The atmosphere itself is toxic, composed of roughly 95% carbon dioxide with small amounts of nitrogen and argon. The oxygen concentration is below 0.2%, effectively zero for human breathing. An astronaut who removed their helmet on Mars would lose consciousness in roughly 15 seconds as the oxygen in their bloodstream was depleted. Death would follow within a few minutes, though the exact cause would be compounded by other factors, because atmospheric pressure would also be fatal at the same time. At around 600 pascals, the surface pressure on Mars is below what is known as the Armstrong limit, the threshold at which water boils at human body temperature. At pressures this low, bodily fluids begin to vaporize. Saliva would boil on the tongue. Tears would boil in the eyes. Moisture within the lungs would boil. You would not explode, despite popular myths, but the damage to tissues would be severe and occur rapidly. Unprotected exposure to the Martian atmosphere would be fatal within approximately 60 to 90 seconds, and those 60 to 90 seconds would be profoundly distressing. This means that every moment spent on Mars requires either a fully functional spacesuit or a sealed, pressurized habitat. There is no stepping outside for fresh air. There is no opening a window because the space feels confined. The boundary between life and death is reduced to a few layers of specialized fabric, along with seals and gaskets. If a suit fails, if a habitat ruptures, you have seconds to minutes to resolve the issue before death is inevitable. This reality applies to every single moment of a surface mission that could last a year or more. And beyond all of this, temperature introduces yet another layer of hostility. On Mars, the average temperature at the surface hovers around -60 degrees Celsius, which corresponds to roughly -80 degrees Fahrenheit. At the poles, during the long Martian winter, it can plunge below -125 degrees Celsius. Even in the most favorable regions, at the warmest moments of the Martian day, the temperature only just struggles to rise above the freezing point of water. The atmosphere is thin, almost vanishingly so, and as a result, heat escapes with remarkable efficiency once the sun sets. The consequence is dramatic. From day to night, temperature variations can exceed 70 degrees Celsius. Every piece of equipment sent to the surface must survive and operate across this brutal range. Lubricants cannot be allowed to freeze solid. Seals must remain flexible rather than shattering like glass. Electronic systems have to function reliably, despite repeated thermal cycling that would rapidly destroy most equipment designed for use on Earth. And the challenges do not stop with temperature. The Martian soil contains perchlorates, chlorine-based chemicals that are toxic to human biology. Perchlorates disrupt thyroid function and, with extended exposure, can lead to serious health consequences. Added to this is the nature of Martian dust. It is extraordinarily fine, far finer than terrestrial sand, and it carries an electrostatic charge. It clings to everything it touches. No matter how rigorous the contamination controls, dust will inevitably make its way inside habitats. Astronauts will carry it in on their suits. It will work its way into seals and settle onto every exposed surface. Controlling perchlorate contamination will be a constant and unavoidable task throughout any extended stay on the Martian surface. That same fine dust poses a direct threat to the systems that keep people alive. Solar panels are expected to provide much of the power for surface operations, yet dust accumulation steadily degrades their performance. The Mars rovers, Spirit and Opportunity both experienced this problem, and both were fortunate enough to benefit from occasional winds that swept their panels clean. Human explorers cannot afford to rely on chance. Active dust removal, whether through mechanical cleaning systems, electrostatic methods, or other solutions, will be essential to sustain power generation. Then there are the planet-wide dust storms. From time to time, Mars is engulfed by storms so vast they can wrap around the entire globe and persist for months. During these events, sunlight reaching the surface is reduced to a fraction of normal levels. In 2018, the Opportunity rover was lost when a global dust storm prevented it from receiving enough sunlight to charge its batteries and keep its heaters operating. Any human mission dependent on solar energy would need either enormous energy storage capacity to endure months of diminished sunlight, or a power source that does not rely on the sun at all. Nuclear power provides such an alternative. Compact fission reactors could deliver continuous, dependable electricity, regardless of dust storms or the cycle of day and night. The Keeler Power Project represents an effort to develop a small fission reactor specifically for space use. Another option comes from radioisotope thermoelectric generators, like those used by the Curiosity and Perseverance rovers, which convert heat from radioactive decay directly into electrical power. Yet nuclear systems bring their own complications, including launch safety concerns, engineering complexity, and political considerations that solar power largely avoids. Water, oxygen, food, energy. Each of these resources must be supplied without interruption for years at a time. Each relies on machinery that has to survive extreme cold, chemically aggressive dust, and relentless radiation. Every possible failure must be anticipated, because Earth is 26 months away. If an oxygen production system fails and cannot be repaired, there is no rescue coming. Suffocation would arrive long before help ever could. Living on Mars is unimaginably hard. But there is another challenge, one that often receives less attention than it deserves: returning home. Unlike the Moon, where astronauts could carry sufficient fuel to lift off and head back to Earth, Mars presents a far steeper problem. Its gravity is significantly stronger, and escaping it demands vastly more propellant. When you examine the numbers, the difficulty becomes stark. The Moon's gravity is about 1/6 that of Earth. To leave the lunar surface and reach orbit, the Apollo astronauts needed to reach a velocity of roughly 1.7 kilometers per second. The ascent stage of the lunar module carried about 2,300 kilograms of propellant to achieve this. The margins were slim, but it was possible within the limits of what could be landed on the Moon. Mars tells a different story. Its gravity is 38% that of Earth, more than twice the Moon's pull. To reach low Mars orbit from the surface requires a velocity of around 3.5 to 4 kilometers per second. But orbit is not enough. There is no nearby command module waiting. To come home, a spacecraft must escape Mars entirely and enter a trajectory back to Earth. From the surface, that demands a total velocity change of approximately 5.5 to 6 kilometers per second. Here, the rocket equation becomes unforgiving. Fuel requirements do not increase linearly with velocity. They rise exponentially. Increasing the required velocity from 1.7 kilometers per second to 5.5 kilometers per second does not merely triple the fuel needed. It increases it by roughly an order of magnitude. With similar engine efficiency, a vehicle capable of returning astronauts from Mars to Earth would require perhaps 30 to 40 metric tons of propellant. And that is only the fuel. You must also account for the tanks that store it, the engines that burn it, the structure that holds everything together, and the life support systems needed to sustain human beings through another 7-month journey across interplanetary space. Now consider what it truly means to deliver that propellant to Mars. Every kilogram must first escape Earth's gravity well, a process that consumes fuel. Then, it must be accelerated onto an interplanetary trajectory, demanding yet more energy. Finally, it has to be brought safely down onto the Martian surface, a task that is among the most technically challenging feats in space exploration. As we have explored, for every single kilogram of propellant intended for the return journey, you may need to launch 10 kilograms or more from Earth. When you include the fuel required to move fuel itself, the calculations quickly explode. Very soon, the total mass involved exceeds anything that any rocket ever built or currently under construction could realistically handle. This is precisely why every credible plan for going to Mars relies on a concept known as in situ resource utilization, or ISRU. Rather than transporting all the return fuel from Earth, the idea is to produce it on Mars using what is already there. If you can manufacture rocket propellant on the Martian surface, you eliminate the need to lift it out of Earth's gravity entirely. Suddenly, the mission shifts from being utterly unfeasible to something that might just be possible. The most widely studied approach uses methane and liquid oxygen as propellants. This pairing, often referred to as methalox, offers compelling advantages for Mars exploration. Crucially, both methane and oxygen can, in principle, be produced on Mars itself. The Martian atmosphere is composed of about 95% carbon dioxide. Water is present as ice at the poles and is also bound within the soil across a range of latitudes. Given these ingredients and a sufficient supply of energy, it becomes possible to generate everything required to fuel a spacecraft for the journey home. The chemical pathway is elegant. First, water is extracted from Martian ice by mining and heating the material. That water is then split into hydrogen and oxygen through electrolysis, using electrical current to break the molecular bonds. The oxygen is stored as a liquid oxidizer for the rocket engines. The hydrogen is then reacted with carbon dioxide drawn from the atmosphere in a process known as the Sabatier reaction, producing methane and water. The methane becomes the fuel, while the water is fed back into the electrolysis system. In theory, tens of metric tons of propellant could be produced using only Martian resources, imported machinery, and energy. The entire Mars strategy developed by SpaceX is built upon this assumption. The Starship vehicle is designed to burn methane and oxygen specifically because these propellants can be manufactured on Mars. The concept involves landing starships on the Martian surface, refueling them with locally produced propellant, and then launching them back toward Earth. Without ISRU, Starship has no way home. With ISRU, the system becomes at least theoretically workable. Yet there is a vast gulf between theory and reality. Producing rocket propellant on Mars demands solutions to a host of engineering challenges that have never been demonstrated at meaningful scale. All equipment must operate reliably in extreme cold. Mining systems have to extract water from frozen regolith or buried ice deposits. Chemical processing plants must function autonomously for months or even years, with little to no maintenance. Cryogenic storage systems must keep methane and oxygen in liquid form despite temperature swings and long storage durations. Every component must achieve reliability beyond anything we routinely manage on Earth, because failure does not merely delay a mission, it strands people. Some early steps toward validating the concept have been taken. The MOXIE experiment aboard NASA's Perseverance rover successfully produced small quantities of oxygen from the Martian atmosphere. Over multiple test runs during the mission, MOXIE generated about 50 grams of oxygen, roughly enough for a single astronaut to breathe for 100 minutes. This demonstrated that the underlying chemistry works under Martian conditions. However, scaling from 50 grams to the approximately 30 metric tons required for a crewed return mission represents an increase by a factor of about 600,000. That leap is anything but trivial. Extracting water poses additional challenges. We know that water ice exists on Mars, but the most accessible deposits are found at higher latitudes, where environmental conditions are harsher and sunlight for solar power is more limited. Sites closer to the equator, which may be more suitable for human activity, could offer far less accessible water. Identifying a landing location that combines tolerable surface conditions with extractable water is therefore a major constraint. In some cases, reaching ice may require drilling tens of meters below the surface, adding both complexity and mass to the mission. Propellant production also takes time, a great deal of time. Depending on the scale of the equipment and the available power, generating 30 to 40 metric tons of methane and oxygen could take a year or more of continuous operation. This has led to mission designs in which cargo vehicles land on Mars, 1 or 2 launch windows before the crew, carrying propellant production systems that begin working autonomously. Only once mission controllers have verified that enough propellant has been produced and safely stored would the crew be allowed to launch. If production fails or falls short, the crew's departure is postponed by another 26 months. If failure occurs after the crew has already left Earth, the situation becomes perilous. This is the central risk of relying on ISRU. It means placing astronauts' lives in the hands of machines that must operate flawlessly on another world for extended periods without human oversight. The systems must endure Martian dust storms, severe temperature extremes, and unforeseen conditions. There is no repair crew to call, no replacement shipment arriving in a few days. Either the machinery performs as intended, or the mission collapses, potentially with fatal consequences. Because of this, some mission planners have proposed alternatives that lessen reliance on ISRU. One such idea involves pre-positioning not only the production equipment, but also propellant manufactured on Earth and delivered to Mars before the crew arrives. This removes the uncertainty of producing fuel on Mars, but at the cost of dramatically increasing the mass that must be launched from Earth and landed safely on another planet. Another idea looks at keeping the return spacecraft in orbit around Mars, rather than bringing it down to the surface. By doing that, the amount of fuel needed to reach it from the ground is reduced, but this choice introduces a new layer of difficulty. Astronauts would have to launch from the Martian surface and rendezvous precisely with a vehicle circling the planet, a maneuver that adds complexity and carries its own set of risks. The most extreme alternative is to remove the return journey altogether. One-way missions to Mars have been proposed in earnest, not as acts of despair, but as genuine attempts at settlement. The people who go would do so knowing they intend to stay, establishing a self-sustaining colony that slowly expands. Seen from this angle, the problem of return fuel simply disappears because there is no return. Every kilogram that would otherwise be reserved for fuel to come home could instead be used to support long-term survival and the construction of a permanent settlement. But this idea opens the door to deep ethical questions. Is it right to send people on a journey they can never reverse? And what if the colony fails to become self-sustaining? In that case, the settlers would rely entirely on ongoing support from Earth, with regular supply missions delivering food and equipment until local production could finally meet demand. If that lifeline were cut by economic collapse, political shifts, or a gradual loss of interest back on Earth, the colonists could face a slow and silent starvation. Living in permanent exile, with no possibility of return, represents a psychological strain unlike anything humans have ever endured. Some individuals might flourish in such an environment, others might find it impossible to bear. For the moment, NASA and most space agencies continue to insist on round-trip missions. The guiding principle of human spaceflight since its earliest days, that we do not abandon our people, applies to Mars just as strongly as it does to low Earth orbit. It is a noble position and one that aligns with our instincts about exploration, but it also makes the mission far more challenging than any one-way journey ever could. The comparison with Apollo is useful, but it can also be misleading. People often ask why we cannot simply scale up what worked for the Moon. Apollo showed that we could send humans to another world and bring them safely home. So why should Mars be so much harder? The answer lies in how fundamentally different Mars is as a destination. Distance changes everything. The Moon is only 3 days away. If something goes wrong, you can turn around and come home relatively quickly, as Apollo 13 so dramatically demonstrated. Mars is about 7 months away. Once you depart Earth orbit, you are committed. Meaningful abort options are effectively non-existent. The spacecraft must carry supplies and redundant systems for a journey measured in years rather than days. With duration, every problem grows. A system that works reliably for 2 weeks may fail during a 2-year mission. Supplies that can simply be packed for a lunar flight must be recycled again and again, or produced locally for Mars. The psychological stress of isolation that astronauts can tolerate for days may become overwhelming when stretched across years. And the environments on the surface introduce further complications. The Moon has no atmosphere. That means no heating during entry, no parachutes, but also no weather, no dust storms, and no atmospheric chemistry to worry about. Mars, by contrast, has just enough atmosphere to create severe difficulties during landing, but not enough to make that landing straightforward. The lunar surface is unforgiving, yet simple. Mars adds layers of complexity. The soil contains toxic chemicals. Dust storms can engulf the entire planet. The atmosphere is close enough to being useful for making fuel to be tempting, but far from easy to exploit. Returning from the Moon was difficult, but it fit within the mass limits of the mission. Returning from Mars demands either enormous amounts of fuel launched from Earth or fuel manufactured on another planet using techniques never demonstrated at large scale. For Apollo, landing marked the completion of the hardest task. On Mars, landing is only the start of a prolonged struggle for survival that must succeed before an equally demanding return can even be attempted. None of this means Mars is impossible. It means Mars is extraordinarily difficult in ways that force us to solve problems we have never solved before. Every challenge does have potential solutions. Those solutions come with costs, risks, and uncertainties. Progress is being made across the board, but anyone who claims that reaching Mars is simply a matter of building a bigger rocket and pushing harder is not being honest about the physics and engineering involved. We have walked through the obstacles, the vast distances that stretch communication and supply lines beyond anything humanity has attempted, the radiation that damages the human body throughout the journey, the physical decline caused by months in microgravity, the frightening complexity of landing massive payloads on a planet with an atmosphere that stubbornly refuses to cooperate, the hostile surface conditions that demand constant protection from cold, near vacuum, toxic soil, and pervasive dust, the immense requirement for return fuel, which must either be launched from Earth at staggering cost or produced on Mars using unproven technology. Each challenge is daunting on its own. Together, they form a barrier that has kept humans confined to Earth orbit for more than 50 years since the final Apollo mission. And yet, progress is real. Measurable advances are being made on problems that once seemed unsolvable. The answers are not complete. The technologies are not yet mature, but the direction is clear, and it points toward Mars becoming achievable within the next few decades. Radiation shielding continues to improve. Materials rich in hydrogen, which reduce the production of secondary particles, are finding their way into spacecraft designs. Concepts for active shielding, using magnetic fields to deflect charged radiation, are being explored, though they remain technically demanding. Perhaps most importantly, nuclear thermal propulsion is once again receiving serious attention and funding after decades of neglect. A nuclear thermal rocket uses a reactor to heat a propellant, usually hydrogen, to extremely high temperatures before expelling it to generate thrust. This method is about twice as efficient as chemical rockets, and that efficiency translates directly into shorter travel times. A mission using nuclear thermal propulsion could reach Mars in about 4 months rather than 7 months. That represents 3 fewer months of radiation exposure, 3 fewer months in which the human body deteriorates under weightlessness, and 3 fewer months of psychological strain. It does not make the challenges vanish, but it reduces them in a meaningful and practical way. NASA and DARPA are working together on the development of nuclear thermal propulsion. The aim is to achieve a demonstration flight in the late 2020s or the early 2030s. If it succeeds, this approach could reshape the entire architecture of a Mars mission, allowing journeys that are both faster and safer than anything achievable with chemical rockets alone. When we turn to the physiological challenges, artificial gravity remains the most compelling long-term solution. There are several proposed designs for spacecraft that rotate in order to generate centripetal acceleration, effectively mimicking gravity. The engineering difficulties are considerable, and the mass cost is high, yet the potential benefits are profound. Astronauts spending the journey in a rotating section of the spacecraft would reach Mars with bones, muscles, and cardiovascular systems far closer to their normal condition on Earth. They would be capable of carrying out demanding surface work almost immediately after landing, rather than needing days or even weeks to recover. SpaceX has suggested that the large internal volume of Starship could permit some form of artificial gravity, although the details remain unclear. Other concepts involve linking 2 spacecraft or spacecraft sections with a tether and rotating them around a shared center of mass. These technical challenges are serious, but they are not beyond our reach. If humanity is truly committed to sending people to Mars, artificial gravity may shift from being a desirable extra to becoming a basic requirement. Landing technology, meanwhile, is advancing at a remarkable pace. SpaceX's work on Starship, regardless of its final success or failure as a Mars vehicle, is providing invaluable experience with supersonic retropropulsion and precision landing. Every test flight, including those that end in failure, generates data that deepens our understanding of how very large vehicles behave during powered descent. NASA continues to develop inflatable heat shields and advanced parachute systems that could broaden the range of payloads that can be landed safely on Mars. The exact solution that ultimately proves successful may not yet exist, but the route toward viable solutions is being actively and methodically explored. In situ resource utilization has now moved from theoretical discussion to demonstrated reality. The MOXIE experiment showed that oxygen can be extracted from the Martian atmosphere using equipment that operates under genuine Martian conditions. The next stages involve scaling these systems up, demonstrating the extraction of water from Martian ice, proving the Sabatier reaction at production rates that matter, and storing cryogenic propellants for long periods of time. Each of these steps will almost certainly be tested robotically before any astronauts are asked to rely on them. The first crewed mission will likely only be launched once automated systems have already produced and stored enough propellant for a return journey. Perhaps most importantly of all, the economics of spaceflight are undergoing a transformation. When the space shuttle was flying, the cost of launching 1 kilogram to low Earth orbit was roughly $50,000 or more. SpaceX has reduced that figure to around $2,700 per kilogram on Falcon 9, and Falcon Heavy lowers it further for larger payloads. If Starship reaches its design goal of full and rapid reusability, that cost could fall to just a few $100s per kilogram. This is not a modest improvement. It represents a fundamental shift in what is economically possible. When launch costs drop by a factor of 100, missions that were once financially impossible become merely expensive. Mass constraints that once forced harsh compromises can be eased. Redundancy that was previously too heavy becomes affordable. Supplies that could never be justified can now be included. The entire logic of mission planning changes when access to space becomes inexpensive. This is why private companies matter so deeply in the context of Mars exploration. SpaceX exists with the explicit goal of making humanity a multiplanetary species, and that is not just a slogan. The entire organization is structured around developing the technologies required for Mars settlement. Blue Origin holds similar long-term ambitions, albeit with different schedules and strategies. These companies can accept risks that government agencies simply cannot. They can fail and learn in ways that would be politically disastrous for NASA. SpaceX has destroyed many rockets during development, and each loss has delivered data that fed directly into improving the next design. This kind of rapid iteration is often how the most difficult engineering problems are solved. Competition also plays a crucial role. China has announced ambitious plans for lunar missions and has made clear its interest in Mars. If China commits serious resources and clear timelines to a Mars program, it could trigger a new era of competition in space. The Apollo program succeeded in part because the United States was competing with the Soviet Union. National prestige was on the line, and political will and funding followed. A similar dynamic involving China could generate the sustained commitment that Mars missions demand. But it is important to be honest about what the first missions to Mars will actually look like, because the gap between science fiction and engineering reality is wide. The first human landing on Mars will not resemble the elegant habitats seen in films and television. It will be far closer to an extreme mountaineering expedition. A small group of people surviving in a hostile environment with minimal equipment, willingly accepting significant personal risk in order to achieve something never done before. The crew will likely consist of 4 to 6 individuals. Larger teams would offer greater redundancy and a wider range of skills, but they would also require more supplies, more living space, and more life support capacity. The habitats will be cramped, and privacy will be almost non-existent. The same few faces will constitute the entirety of human contact for years. Entertainment options and psychological support will be limited by constraints on mass and communication bandwidth. The food will be monotonous, optimized for nutrition and long-term storage rather than enjoyment or variety. The work itself will be physically exhausting and mentally demanding. Surface operations will involve long hours in spacesuits, digging into the soil, deploying and repairing equipment, conducting experiments, and constantly maintaining the systems that keep the crew alive. Equipment will inevitably fail and will have to be repaired using only the tools at hand and whatever spare parts happen to be available. Medical emergencies will arise, and the crew will be forced to deal with them largely on their own, with limited supplies and advice arriving late from Earth. The reality of death will be present every single day, from mechanical breakdowns, from accidents, from medical crises, from any of the many ways Mars relentlessly threatens the fragile human body. The astronauts who choose to take part will be remarkable individuals, not only physically strong and technically skilled, although they will certainly need to be both. They will require a level of psychological resilience far beyond anything we have seriously tested before. For years at a time, with no possibility of escape, they must operate effectively within a very small team under constant and extreme pressure. they must also accept a stark truth: they may never return. The mission could fail in ways that leave them stranded or dying on another world. And yet they will go, because some humans are drawn to frontiers, because for them the chance to be first outweighs the promise of safety. I believe we will find people like this. History tells us we always do. Someone was the first to cross every ocean, the first to climb every mountain, the first to explore every cave system, ice sheet, and desert. The motivations differ: curiosity, ambition, restlessness, the desire to see what lies beyond the horizon. But the willingness to accept danger in exchange for discovery appears to be a constant feature of our species. Mars will draw exactly that kind of person. What makes Mars such a strange and beautiful destination is what it represents for our understanding of life in the universe. Billions of years ago, Mars may have been habitable. Liquid water flowed across its surface. Its atmosphere was thicker, its conditions far more benign. If life arose there independently, even simple microbial life, it would fundamentally change how we think about the prevalence of life throughout the cosmos. To find evidence that Mars was once alive, or perhaps still shelters life in underground reservoirs of water, would rank among the greatest scientific discoveries humanity has ever made. And this search can only truly be carried out by humans working directly on the surface. Robotic explorers are extraordinary machines, but they move slowly and their ability to analyze is limited. A trained geologist can survey a landscape and instantly recognize the most promising sites for investigation, something that could take a rover months to achieve. Human intuition, adaptability, the capacity to notice the unexpected and act on it immediately. These are precisely the qualities required to search for traces of past or present life. Robots have paved the way. Humans will finish the task. But there is another reason Mars matters, one that speaks to the long-term future of our species. Earth is magnificent. It is the only home we have ever known, the only place where humans can survive without technological support. Yet Earth is also more fragile than we like to admit. Asteroid impacts have triggered mass extinctions before, and they will happen again. Supervolcanic eruptions have the power to cripple global civilization. Our own actions are altering the climate, introducing new and growing risks. And on sufficiently long time scales, the sun itself will change, slowly growing brighter until Earth can no longer sustain life. A species confined to a single planet is inherently vulnerable. A multiplanetary species is not. If humans establish a truly self-sustaining presence on Mars, one that does not rely on Earth for survival, then extinction becomes far less likely. A catastrophe that ends civilization on Earth would not necessarily end humanity. With populations living on both Earth and Mars, separated by millions of kilometers, it is improbable that both would be destroyed by the same event at the same time. This is not an argument for abandoning Earth. Earth will remain our home for the foreseeable future, where most people live and where our civilization is rooted. But having a second foothold, a place where humanity could survive and rebuild if necessary, offers a form of insurance against existential threats. The cost of creating that insurance is immense, but the reward is the continued survival of our species across time spans measured in millions of years. Mars feels impossible, just as many of humanity's greatest achievements once did. The obstacles are real. The laws of physics are unforgiving. The engineering demands exceed anything we have yet proven we can accomplish. Every system must function. Every problem must be addressed. Every risk must be accepted or reduced. The margins are narrow and the stakes could not be higher. Yet we have faced impossible challenges before. We crossed oceans without knowing what awaited us beyond the horizon. We built flying machines after respected scientists declared heavier than air flight impossible. We sent humans to the moon using computers less powerful than a modern calculator. Each time, the impossible redefined what we believed could be done, and in doing so opened the door to even greater achievements. Mars is the next such challenge. The distances are immense. The journey is long. The world we arrive at is hostile, and the return is uncertain. Everything about the mission presses against the limits of our knowledge and capability. And that is precisely why it matters. Not because it is easy, but because it marks the current frontier of human potential. Reaching Mars would show that this frontier can be pushed further than ever before. The astronauts who eventually stand on its surface will look up into a butterscotch-colored sky and see Earth as a faint blue point in the twilight. They will know that everyone who has ever lived, every civilization that has risen and fallen, every story ever told, unfolded on that tiny speck of light millions of kilometers away. And they will know that they have taken the first step toward making humanity something larger than a single planet. That step will be worth taking, whatever the cost, and however long it takes. The impossible is simply what we have not yet done.